Hello students and welcome to a new lecture. In this chapter we will be learning about molecular geometry and bonding. We are going to discuss VSEPR theory, which is valence shell electron pair repulsion model. That model will allow us to predict the three-dimensional shape of molecules. The model will predict the geometry of the molecule, and it is based on the fact that electrons repel one another, so we try to place them as far apart as possible from each other. There are two rules that we're going to be looking at. Double and triple bonds are treated like single bond because these are electrons that are going in one direction, which is the direction towards the other atom we are bonding to. So it doesn't matter if we are having 2 electrons, 4 or 6, because these electrons are in one location, right? They are going to the atom that the central is trying to bond to. If molecules has resonance structure, you only have to apply the theory to any one of these resonance form, and that will be the shape of the molecule. Now, in order to be able to predict the molecular geometry, step 1, we do have to draw the actual Lewis structure. Then we have to determine number of electron groups. So what are electron groups? These are the bonded atoms and lone pairs. So if I'm asking you that surround the central atom, if I'm asking you how many electron groups are there, you only have to look at the central atom and see how many atoms and lone pairs around it. So that will show you examples and we will be calculating this together. Then we place electrons or electron groups as far apart as possible from each other. For bond angles, remember that with the lone pairs are more repulsive than bonding pairs, which means they are gonna be repel more, which will change the angle, as I will show you once we go through specific examples. Okay, so now let's identify number of electron groups. Beryllium, it is the central atom. How many electron groups around it? Remember how we calculate that? It is number of atoms and lone pairs on central atom. So beryllium, it does have 2 atoms around it and no lone pairs. Therefore, beryllium will have 2 electron groups. Water, how many electron groups does water have? Well, 2 atoms and 2 lone pairs. If you add them up together, 4 electron groups. Now, the theory, again, if I want to simplify the theory to you, the bonds and the lone pairs, what do they have in common? They are made of electrons. So the electrons had to be placed as far away from each other as possible. And I don't care if those electrons are in a bond or in lone pairs. Electrons are electrons. They are going to repel each other. So I have to place them as far away from each other as possible. This molecule here, right? How many electron groups does it have? It doesn't have any lone pairs, but it does have, let's look at this one here together. It does have 3 atoms, right? No lone pairs, so 3 electronic groups. Did it matter that this is a double bond and this is a single bond? The answer, no, it didn't. Why? Because again, these are going in one direction, in one location. I still gonna have to separate them as far away as possible from the other electrons in the other bonds. It doesn't matter if I am separating 2 or 4, I still have to separate them as far away from each other as possible. Okay, so now we have learned how to calculate number of electron groups. Now we're gonna start looking at models. And first column, we will have the number of atoms bonded to the central atom. The second one, number of lone pairs on the central atom. Then what we call the electron geometry, and then the molecular geometry, and then finally I'm going to show you how we predict the shape. Beryllium dichloride. How many atoms bonded to the central atom? 2. No lone pairs. So I have 2 electron groups. What is the best separation to put them as far away from each other as possible? The best separation will be 180 degrees. So that makes the shape to be linear. So the electronic shape shows how electrons are put around the central atom, whether these electrons are bonding electrons or lone pairs, they are again pairs of electrons. Molecular geometry is what we see the atom relationship to each other. And the atom relationships to each other is also a linear relationship with an angle of 180 degrees. So, take a note. If there are no lone pairs on the central atom, electronic and molecular geometry are the same. Here is the shape of beryllium chloride, and carbon dioxide also falls in this category. Look at the Lewis structure. You have two atoms around carbon, which means two electronic groups. They will be separated by 180 degrees. Electronic and molecular geometry is linear. Next model. Look at formaldehyde. 3 electronic groups, right? 3 atoms around the central atom, no lone pairs. What is the best separation of the 3 things around the central atom? That will be trigonal planar, right? It's a triangle on the plane of the page or the screen you're seeing that will separate them by 120 degrees. The molecular geometry is also trigonal planar. Now, let's look at the shape of boron trifluoride, which is under the same category. Remember, this is an exception to the octet rule because boron group 3A is good with 6 electrons. That will be the shape of boron trifluoride, trigonal planar. Next model, methane. When you draw the Lewis structure, there are 4 atoms bonded to the central atom, 0 lone pair. Now, what is the best separation? In this case, the best separation is a 3-dimensional shape that is called tetrahedral. Tetrahedrals are separated by the magical angle 109.5 degrees, right? It is better than doing a 90-degree separation because the further away from each other, the less the repulsion is and the more stable the molecule. I want to show you how to draw this in a 3-dimensional way. So if I have A, then the first 2 bonds are these 2 bonds separated again by 109.5, which is slightly bigger than 90. Now there is a bond sticking towards you outside of the screen surface, and there is a bond going away from you behind the screen surface. Okay, that is the shape of tetrahedral, and that makes it 3-dimensional because only if this is atom B, atom B, atom B, and atom B, only these 3 atoms are on the plane of the screen. This one, the wedge, is sticking outside of the screen going towards you. The dashes is going away from the screen, back from, to the back, away from you. Okay, and that is the shape of tetrahedral. Again, molecular and electronic is the same. This is again, guys, if you can see it now here, you will see how, let me just clarify this. You see how you have here, these 3 are on the plane of the screen, right? Then you have this one sticking out towards you and this one away from you to the back. This is the shape of tetrahedral. Next model, we have exceptions to the octet rule, which is an expansion of the octet when we go to period 3. You will have 5 atoms bonded to the central atom, 0 lone pairs. Now that gives the shape that we call trigonal bipyramidal. So the molecular shape will also be trigonal bipyramidal. Now we have 2 types of angle in this shape. We have the equatorial bonds and the axial bonds, which will give me 2 angles. So let me show you that now, okay? These 4 atoms are on the screen surface, okay? So these are planar, on the plane of the screen. This is a wedge going towards you, and this is a dash going away from you. Those 3 bonds here, let me erase that. Those 3 bonds that are coming from the center, Those are called equatorial. And they are separated from each other by 120 degrees. Now, these two here, these are axial. And the angle between the axial and the equatorial is 90. So I have two different of bonds. I have the equatorial bonds and the axial bond, which leads to two different angles. 120 between the equatorial ones and 90 between the axial and the equatorial. This is how you draw this on the paper. So again, if this is your central atom, then you have 4 bonds on the plane, right? Sorry, four atoms on the plane. Then you have one coming towards you and one going away from you. Now, if you see this drawing here, right? So you are making one pyramid here. That's one pyramid. Let me clean the screen so you can see it, okay? So if you connect the base is a triangle. Then if you connect the base to the top atom, you build one pyramid. And if you connect the base to the other atom, you build the other pyramid. So you have 2 pyramids with a triangle base. Therefore, the shape is trigonal because there are 2 pyramids, by pyramidal. Next model is sulfur hexafluoride. And now we're going to look at, this is another exception to the octet rule and expansion to the octet. 6 atoms with 0 lone pairs. The shape for that will be octahedral. In the octahedral, the angles are 90 between the ones in the equatorials and the ones axial and equatorial. So therefore, actually, because the angles are identical either way, there is really no axial and equatorial. All bonds are equivalent. Okay, so now let me show you the summary of the bonds. This is here the octahedral. And in octahedral, guys, you can see here that the angles are 90 here and 90 here. So really there is no axial or equatorial, because if you start to rotate the molecule, whatever used to be equatorial will become axial, whatever becomes axial become equatorial with the same angle. How do you draw that? You're going to have a central atom. Then you're going to have 2 going on axial or vertical. And then the ones here, 2 here going forward towards you and 2 going backward away from you. Okay, remember that there is only one kind of angle, which is 90 degrees. Okay, here is another way to look at all these shapes. And this is again a table that summarizes the shape and the angle as we have gone through all of them, from linear to trigonal planar to tetrahedral to trigonal bipyramidal and octahedral. In the next part, we're going to be adding lone pairs, which will affect the molecular geometry, but the electronic geometry will be the same, right? Because electrons, we're just looking at electrons. Molecular is when we're going to start to notice some changes. Okay, now I have mentioned this before. I'm going to just remind you of it. Lone pairs are more repulsive because they are not contained in a given specific place between 2 atoms. They have more space to expand themselves. So now let's look at the new models in which I'm going to start to incorporate lone pairs. So in this model here, I have 2 atoms around the central atom for sulfur dioxide, however, 1 lone pair. Electronically, I do have 3 electron groups, right? Because electron groups is adding number of atoms and lone pairs. So electronically, what is the electronic configuration of 3 electron groups? That's trigonal planar, right? Because I'm looking at electronic configuration, which means I'm looking at the electrons, whether the electrons are bonds, which is these electrons right here, or lone pairs. These are 3 pairs of electrons I need to separate. The best separation will be what? Trigonal planar. However, if I'm looking at the molecular geometry, it means I'm only looking at atoms. And in this case, if you look at the atoms, if we are only concerned about the shape of the atoms together, then that is bent. However, this bent is bent by an angle of 120. And the reason why this is the angle we are going to look at, because this angle is, determined by the electronic configuration. So what configuration will, or what geometry will determine your angle? It's always the electronic, because the electronic sets what angles are there between the electrons, right? So since my electronic shape was trigonal planar and the angle for trigonal planar is 120, then these atoms will be linear, separated by 120 degrees. Now, next here, we're gonna be looking at molecules with 4 electron groups, right? So we have methane, 4 atoms, ammonia, 3 atoms and one lone pair, water, 2 atoms and 2 lone pairs. Now, all of them electronically, they are all the same. They have to be tetrahedral because electronically they have 4 electron groups. The best separation is 109.7. However, I have mentioned that lone pairs are larger, and if you look at the picture, I'm trying to show you that they are larger. Because they are larger, they are going to push these atoms to get closer to each other, which will make this angle slightly smaller than 109. Here, because I have 2 lone pairs, they push even further, so you can see that this angle now is even less than 109, more than ammonia case, right? In the Chem1A class, if you just tell me less than 109.5, I am good. You don't have to remember 107 and 104.5. Just let me know that it is less than 109 because of the lone pair. All right, so now let's go to the next model. Ammonia, 3 atoms around the central atom, 1 lone pair. Electronically, it's tetrahedral. However, when you look at the atoms, the relationship between the atoms, these are making a pyramid with a triangle base. So that will be trigonal pyramidal. The way to draw this will be, so remember, ammonia is lone pair and 1 atom. These 3 are on the plane of the screen, and then you have 1 coming forward, 1 going backwards, because remember, just think of this one as a bond that you don't draw, right? A bond to the lone pair. So you're just trying to draw tetrahedral if you take into account the lone pair. Okay, so this is again the shape, and you can see in this picture here what I mean when I say it is a pyramid with a triangle base. Therefore, the name of that is a trigonal pyramidal. Next model is water, 2 atoms around the central atom, 2 lone pairs. Electronically, it's tetrahedral. However, when you look at only the atoms, it's bent. But this bent is bent by an angle that is slightly less than 109, not 120 like the previous bent. Why? The angle is determined by the electronic shape. The electronic shape is tetrahedral, which means the angle for tetrahedral is 109. Because of the lone pair, this happened to be slightly lower than that. Okay, so this is the bent shape of water. Now, this is a recap of everything that we talked about, and so far we have covered the 2 electronic groups, 3 electronic groups, 4 electronic groups, with and without lone pairs. Now, next we're going to be covering the 5 electronic groups with different lone pairs. So, here is an example. If you draw the Lewis structure of sulfur tetrafluoride, you will find that you have 4 atoms around the central atom and 1 lone pair. Electronically, it's a trigonal bipyramidal, because that's what we do for trigonal bipyramidal when you have 5 electronic groups. However, molecular will have to depend on the atom relationship to each other. And remember, in a trigonal bipyramidal, we have two types of bonds. We have the axial position and the equatorial position. It is not random where the lone pair will go. Nature make the decision based on what is more stable. And what is more stable is to put the lone pair on equatorial position. Okay? So, turned out you cannot put lone pair on the axial. It is more repulsive. Nature chose it to be on the equatorial position. Now, this will be the new shape right now. And because of that shape, you will see that the lone pair is on equatorial. And now what we have here is two angles, because remember, angles are determined by what again? Angles are determined by electronic shape. This one is slightly lower than 120, and this one is slightly lower than 90 because of the presence of the lone pair. So that is not perfect tetrahedral. If they were tetrahedral, it will be 109. So that make it be called seesaw, because it does look like a seesaw, or another name for it is distorted tetrahedral. Here is how you draw it on your own. Remember, you have the two axial position, and then you have another one on the on the plane of the screen. Then you have one going forward and one going backward. That is the shape of distorted tetrahedral or seesaw. Next model, chlorine trifluoride. You draw the Lewis structure of this molecule. You will find that you have 3 atoms around the central atom, 2 lone pairs. The electronic shape is trigonal bipyramidal. Again, electrons not randomly placed. They do have to go on the equatorial position. That will allow us to have what we call T-shaped. So this is the T-shaped because this is here, if you look at it, it's the letter T, right? If this is your central atom, this is the 3 atoms that are bonding. And then here you have the 2 lone pairs. One of them is going, away from the screen. One of them is out of the screen. But this is how you draw it. Now, let's look at the next model. And if you draw the Lewis structure, you're going to have to appoint one of these iodine to be the central atom, which means you're going to have the other 2 around it, and that will put 3 lone pairs around the central atom. Electronically, this is a trigonal bipyramidal. However, if you look at the molecules, you cannot see the lone pairs. We're only looking at the atoms right now. That is linear 180-degree separation. Now, let's look at the next model, in which we have the 6 electron groups. If you draw the Lewis structure of a bromine pentafluoride, you will find that a bromine has 5 atoms around it and 1 lone pair. In octahedral, all positions are equal, so you're just gonna put one of them. It's easier if you just choose the one either at the top or at the bottom. That will lead to this shape right here, right? Electronically, it's octahedral. However, if you look at the shape of what's left, it is a square pyramidal. And if you look at it carefully, you will see that you have a square base right here, and then you start to connect it, and that will give you a pyramid with a square base. The way to draw this on the paper will be as the following, right? Remember, this is how I taught you how to draw it. So you're gonna have the B. Remember, the other one is where you're gonna put the lone pair, right? So then the other bonds are 2 forward, 2 backward. And that shape is what we call square pyramidal. The angle is slightly less than 90 degrees because of the presence of the lone pair. Next model is xenon tetrafluoride. Xenon is the central atom with 4 atoms around it, 2 lone pairs. That is going to give me octahedral. Now, although all positions are equal, when you put one lone pair though, you have to separate the other lone pair because you have two options. Do you want to separate two lone pairs by 90 degree or 180 degree? And of course, because lone pairs are so large, if you put one here, you do not want to put the other one here. Rather, you want to put it 180 degree away just to maximize the separation. Okay? So electronically, it's octahedral. However, if you look at what's left, you only have a square on the plane, right? And that will be called square planar. And that is exactly how you draw that. Now, this is a summary again for all these two models of 5 electron groups and 6 electron groups with the possibility of lone pairs. Now, geometry of molecules with multiple central atoms, that is very difficult to predict. So what I tell my students, take one central atom and decide what's the geometry around that specific central atom, and then describe around every atom. So I'll give you an example here. So if I have this molecule, and I'm asking you to tell me what's the geometry of this molecule, it's very hard to tell as a whole. However, there are two central atoms. So what I do, I take this central atom and I see what I have. Oh, I have 4 atoms around this central atom, which means the geometry here will be tetrahedral, no lone pairs. Then I go to the second central atom, okay? And I say, okay, this central atom, what do I have? I have 4 different atoms around this central atom. Therefore, the geometry around that central atom is tetrahedral. All right. What are the molecular geometries of aluminum triiodide and sulfur tetrachloride? That means you do have to first write the correct Lewis structure, so you know how many bonds and how many lone pairs are there before you can predict the geometry. So you can pause the video right now and write down or draw the Lewis structure. Now, if you did everything correctly, you know that aluminum iodide has, this is the Lewis structure of aluminum triiodide. If I want to do geometry, I first have to examine the molecule. It has 3 electronic groups, no lone pairs, because aluminum is the exception of 3A group. So therefore, it has to be separated in 120 degree, making the shape to be trigonal planar. For sulfur tetrachloride, if you do the Lewis structure, this is what you will find, that you have 4 atoms and 1 lone pair around the central atom. That means 5 electron groups. Electronically, that is a trigonal bipyramidal. However, you're going to have to do the molecular geometry. So first, I draw the trigonal bipyramidal. I have to put the lone pairs on an equatorial, so I put it here, and then the rest will be atoms. Now that I knew where the lone pairs is going to go, I'm just going to go and place it on the central atom. And this shape is distorted tetrahedral or seesaw. There are 2 angles here. There is this one, which is slightly less than 120, and then there is this one, which is slightly less than 90 degree. In this case, it's a perfect 120 degree. Okay? This will conclude the VSEPR lecture, and I will see you in the next one.